Looks fixed. Thank goodness. All right. Okay. So in general, we've talked about 4 shapes. There's a 5th shape, that one, that I may or may not have mentioned much. I'm not going to ask you about that one this time. Delete that. All right, so if you have these 4 shapes, and we call them A, B, C, or D, or we'll just refer to them by their names, which one of these shapes does like input-output, printing to the screen or the input statement?
The first one. Third one.
First one counting which way? Okay, yeah, that one. That's the input-output. Lucidchart calls it data. We call it input-output because that's what it does. Which one of these is good for decisions, like if or while? Diamond, yep. Which one of these do we use as a start or a stop?
The first one.
Yeah, the oval. The terminator, they call it here. And that kind of leaves the last one as the answer. But what's that block for?
Processes.
Process, right, math, conversions, that kind of thing. All right. We've talked about errors a little bit, and if we go back to the first 2 chapters, I think it's in the first chapter of How to Think Like a Computer Scientist, we've listed 3 kinds of errors. What's a kind of error? Yeah, the easiest one to remember is syntax. That's an error in the grammar of the program. Grammar or a typo, that kind of thing. And the program is really, or idle at least, and a lot of the other editors are not always super clear about showing you where the error is. I'll give you an example. Come on. Like we did one of our in-class assignments with the DEF statement. And that's not going to be on the exam, but we're going to see more of this later. This is called writing functions. The syntax for it is something like this. DEF followed by TEST followed by parentheses followed by a colon. Then, say we just had a print statement. This is all it was going to do. All I want to do is have some fun, whatever. All right, and then down here, somewhere I call test. Or I do A is equal to test, or whatever. I'm thinking I'm pretty cool. I'm going to run it. And it highlights that. And you go, what in the world was wrong with that? It's just an A. How could that possibly be wrong? Well, what is wrong with it? Yeah, we didn't close the parentheses. And that can sometimes be kind of subtle to pick up. But the problem is it was expecting a closed parentheses. It didn't find it, and so it told you about the first non-parentheses character. The first non-parentheses character happened to be a couple lines below it. So it highlighted the wrong line. You just have, that's a learning process. Anyways, that's a syntax error. Then, do we remember another kind? Yeah, logic error. Logic, you're right there too as well. Also, the text calls it a semantic error. I use both terms. You know, I call it a logic/semantic error in the exam. That's when the program runs. There's no syntax errors. It just gives you the wrong output. You type in it's -20 degrees, and it tells you, hey, this is great weather to wear a tank top. You know, stupid thing like that. Yeah. That would be when your character dies, even though you didn't hit anything. You know, in a video game. You know, nobody near him. All of a sudden, his health drops to 0, or whatever. You know, or your program walks through walls. The program's not behaving right, even though it's not displaying any error messages or blowing up. Speaking of blowing up, runtime error. That's the third kind of error. What's a runtime error? That's when the program blows up. It hits a state that it does not expect. And I'm sure your Windows users have seen the classic error message, application has made an illegal instruction and will shut down. And you go, okay, great. There went my thesis, or whatever. So runtime errors are when it can't open a file. It's got a bad file name, or the hard disk is full, or you've disconnected your flash drive, or it's trying to access the internet, but the internet is down. It'd be a real drag if you were accessing Google, you had 20 tabs open, and then it couldn't open Google, and so the application quit. You lost all your tabs. Or you were trying to save your document, save your master's thesis, and it hit an error. Temporarily, the drive was disconnected. It blew up. It crashed the program, and you lost your thesis. You'd really hate that. So, back in the olden days, one version of Word would delete your file before it saved the new version of the file, which is really a bad idea. What if something happens in that split second where the file is deleted and a new one is being saved? You lose your file. That was way back in the late 80s. We don't have to worry about that anymore. Instead, it creates temporary copies of files, and then sometimes people will upload a file. If you say, if you call your program, your file, myfile.docx. I haven't had this happen in this class. We don't use Word docs much. You'll see a file like that created, especially if you haven't saved your document in closed Word. People will upload that, and it's just got garbage in it, and I can't read it. So, haven't seen that happen. Anyways, that's a runtime error. Program hits an unexpected state. When I say hit, that's colloquial. And cannot proceed. Once you learn more about programming, you can figure out how to make it be able to proceed. Google doesn't crash just because it can't open a web page. Excuse me, Chrome. Word doesn't crash just because a hard drive has been disconnected. Other examples of runtime errors. Divide by zero. That's kind of the classic one. There's all sorts of silly memes about divide by zero. Never divide by zero, ever. Divide by zero, oh shoot. Dividing by zero, just one thing not recommended to be done without supervision from Chuck Norris. Whatever. Time paradox, I divided by zero, oh shoot. I'm substituting a word there. Anyways, you get the idea. Dividing by zero will cause your program to crash if it is not handled. I'm going to go back into Python, set up a divide by zero thing. A is equal to input, give me number. And you really don't have to type these examples unless they're helping burn into your brain. A is equal to int A. B is equal to 1 divided by A. We're going to get the reciprocal value of it, and then we're going to print B. Great program. No syntax errors. Logically, it's sound, because it'll work. So let's run it. All right, give me a number, 10. Well, 1 over 10 is 0.1. Now, when you, the programmer, run your program, you almost always give it good data. Why? Because you want to see your program succeed. That's why programmers are pretty bad testers of their own software. I mean, yeah, you know what it's supposed to do. And once you learn ways, that are likely to crash your program, you may test those. But typically, you run it to prove that it works. To write a reliable program, you also have to run it to try to break it. You have to make sure that it can handle bad input, that it doesn't get a runtime error. Here's an example of bad input. There's 2 different places this one could fail. Guess what they are? Even besides divide by zero, there's another one. Yeah, it's wanting an int. It's trying to convert it to an int. That's not going to work if you type in something with a decimal, even if it looks like a whole number. It blows up. That's why in a lot of our programs I just automatically cast to float so that it'll accept, decimal input as well as whole numbers, integers. And the last one is the divide by zero. I type 0. Well, 1 divided by 0 is infinity or something. To infinity or beyond, it blows up. So those are examples of runtime errors. And it's not really your fault as a programmer that you can't convert a floating point number to an integer. That's just the language blowing up, but you have to be able to accommodate it. And when I say you have to, we will learn methods, hopefully, of dealing with that kind of thing. Certainly, if you go on and take scripting, the next course after this, then we will get into how to handle things like that. And you would also learn in Java or C++. Mostly it involves inspecting that data to make sure that it's valid, or for using some kind of code that's called try-catch or try-except that catches runtime errors when they occur and then lets you try to fix the problem. Stops the program from blowing up. So if that application has said an exception has occurred and Windows is shutting it down, if that one had exception handling in it, then it wouldn't crash like that, hopefully. So that's a runtime error. Unexpected state and cannot proceed. If you in your code handle the runtime error, it's no longer a runtime error. You know, you try to save to a file and you put a bad file name, or you try to access a hard drive that doesn't exist. If your code doesn't blow up, if it doesn't crash when that happens, it's no longer a runtime error. It's just a state that you handle. Alrighty. That makes sense. 3 kinds. We'll remember them. Now, there are several questions I'm going to have to remove because of a missing lecture. More than I wished. Way more than I wished. Just means that there's going to be some more simple questions. Alrighty. Remember PEMDAS. I'm going to kind of break it up. PEMDAS. There's a reason I'm breaking it up like that. What does the P stand for? And this is with regard to performing math. Yeah, these are the parentheses. Parentheses have to be resolved first when an expression is being evaluated. What's an expression? A math equation or whatever. What does E stand for? Exponent, which in this one, how do we do exponents in this language? Star, star, right. And then multiplication and division, MD, have equal priority, equal precedence. So they're just done left to right. And why is that? Because it doesn't really matter what order they're done in. If you do this, 20 divided by 2 times 3, well, no, I want to come up with a better example than that. There we go. It doesn't matter whether you do this part first or whether you do this part first. Because 20 divided by 10, 20 divided by 2 is 10. Then you multiply it by 5, you get 50. Let's do the other one first. It does matter. Okay, it has to be done left to right, but it doesn't matter which ones occur first. It's not like it searches for all the multiplications and then for all the divisions. That makes sense? We'll do some examples of that. And then addition and subtraction. So, star, division. There's another kind of division called floor division, which we will mention again. And then there's modulus. So really, multiplication and division cover a lot of things. But when we learned this, you know, in junior high or whatever, whenever we learned our order of precedence, we weren't using a computer language, so we didn't have floor division or modulus. That means floor division, what does what? If I do this, 3 divided by 2, what's that going to equal? 3 divided by 2 is equal to 1.5. What's 3 floor division equal to? What's floor division mean? It means round down. So what's 3 divided by 2 rounded down? 1, right. And then modulus. Modulus means what's left over after you do the floor division. In this case, it's going to be the same thing, right? 3 modulus 2. Well, 2 goes into 3 one time with a remainder of, did I hear 5? I see why you said 5. No, it's after you do the floor division. 2 goes into 3 one time, leaving 1. That makes sense? So, what's 4 modulus 2?
0.
Yeah, that's 0 because 2 goes cleanly into 4. Nothing left over. We know the idea of remainders because if you do the, like this, and you divide like that. 5 goes into 11 how many times? 2. Okay. 2 times 5 is 10. What is our remainder? 1. Right. So 11 modulus 5 would be 1. So 11 modulus 3 is what?
2.
2. It's 2. Right. Everybody see why? 3 goes into 11 3 times. 11 minus 9 is 2. Okay. So that's our reminder about PEMDAS. And then addition and subtraction, which we know those symbols. This is certainly not new to us. All right, so some expressions just to test ourselves. 2 plus 3 times 4. 2 times 3 plus 4. 2 times 3 plus 4. That kind of thing. 2 star star. 4 minus 3. All right, let's figure out what these are. What needs to be done first there? Multiplication. So that's 3 times 4 is 12. What's 2 plus? That's 14. So guess what? Multiplication has to be done first here. Yep, so 2 times 3 is 6, plus 4 is 10. What gets done here first? Well, we got to resolve the parentheses. So 3 plus 4 is 7, times 2 is 14. Interesting that it came out the same as that. Anyways, what about here? PEMDAS. Well, we see some exponents, but even before the exponents can be handled, what do we have to do?
4 minus 3.
Yeah, the 4 minus 3, which is 1, and 2 to the power of 1. Well, any number to the power of 1 is its same number. I'm not trying to make this a weird math class, but n to the power of 1 is equal to n, just like 4 to the power of 1, because it just means 4. It's multiplied by itself, not even once, you know. N to the power of 0, a little quiz, is 1. Doesn't matter what n is. N could be negative 6,000. If you raise it to the power of 0, it's 1. And I could sit up there and draw on the board why, but you don't care, neither do I. So then n to the power of 0.5, this isn't going to be on the exam, by the way, is equal to the square root of n. That's a quick way to figure out the square root of something if you can't remember the name of a square root function. All right, a variable has 3 components. It's got a name. Every variable has a name. What else does a variable have or is keeping track of behind the scenes? Well, when I do this, A is equal to int A. If they had typed in 10, what is A going to be when we're done? It's going to be 10. So every variable has a name and it has a value. And then what else does it have? What else have we been caring about? Why did we bother with that? What does that keyword do? What does that function do?
Makes it a whole number.
Yeah, it makes it a whole number, just like if we had done A is equal to float A. Right? We've been using A is equal to float A since about, day 3. What does that do? It takes A and turns it into a floating point number. Well, why in the world does it do that? Because it's not a number at all when you type it in. It's what's known as a string. And you can't do math on a string. The computer doesn't know whether you typed in 10 or whether you typed in McGillicuddy, Can't do math on it. It has to be converted to a number. That means that every variable not only has a name and a value, it has a type. And the types that we have discussed are ints. What's another one? Floats, and then strings. Strings are what we get from the input command. Ints and floats are what we can do math on. In some languages, you have to declare your variables before you use them. This is just for your information. You have to say int x before you put a number in x. And you certainly don't have to type this. This is like in C or C++ or Java. Once you declare your variable in one of those languages, you can't put anything of the wrong type in it. You couldn't say x is equal to 10.3. The compiler checks, the language checks and goes, oh, you already said it was an int. You're not fooling me. I can't take anything else other than an int. Or, I know that y is a float, so you better not say y is equal to Fred, with quotes around it. That's called a declaration, or type declaration. We don't care in this language. In this language, doesn't matter. You can store an int in something 1 second, and you can store a string in it the second. That's what we do here. We get a string called a, and then we immediately turn it into a number. Stick it back in the same variable. That wouldn't be possible in a more strictly typed language. If I go too fast, let me know if you have questions. That's why I'm trying to ask questions as we talk about these things. Alrighty. Write a single line of code. Well, let's not make it necessary to say single. Write some code that asks the user for their name and stores it in a variable called name. Good variable name. The message displayed should be, what is your name? Okay, how would we do this? We've learned more than one way of doing it. So if you tell me one way, I'm not going to tell you that it's wrong.
Print.
Yeah, we'd use a print statement. What are we going to print? What is your name? Question mark. Then, now we want to ask the user for it, so
Name equals input.
name is equal to input. I think I heard n is equal to. That would be correct if I'd done that. And it's not like I'm going to count you totally off if you use the wrong variable name. But since I specify a variable name, you may as well follow it. If I had asked this question in the form of like this, write some code that asks the user, or write a single line of code that asks the user for their name, blah, 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 blah. We can condense that to a single line of code. How do we do that?
Name equals input with the question inside the parentheses.
Right, because the input statement can accept a string right here, and if you give that a string, it prints that out. So the printing before it is not quite necessary. We could just do this. Name is equal to input. What is your name? Hopefully that makes sense. We've been doing that for a long time, except we've been asking for numbers more than strings. And we all know how to do stuff like this. Write some code that asks the user for their age, converts it to a float, and stores that result in a variable named A. I don't even really think I need to go over that, right? Or does anybody? Come on, guys, raise your hand if you care. I mean, not if you care, but if you don't know how to do it. Or just cough loudly so I won't know who did that. Okay, I've fished enough. Let's go on. All right, there's a difference between a single equal sign and a double equal sign. What does a single equal sign do?
Assign.
That's called assign or assignment. That's the same thing as set in our pseudocode. Assignments are things like A is equal to 3 or B is equal to X times 2, that kind of stuff. The equal sign means take whatever's on the right side, copy it over to what's on the left. Then there's the double equal sign. And that's compare. Compare for equality. Now, when we're talking about these colloquially, or when I'm reading them off during code, and I know I've said this before, I may say type A equals 3, and then type if A equals 3. I use the same words. Why? Because that's just the way the English language works. If I remember, I'll say if A equal 3. But if you typed this, if you typed either one of these statements, A equal 3, that's a syntax error, because that's a comparison that it can't do at that point. You know what? I'm not totally sure that that's true. What happens if I type in A equal 3 right here? Okay. It doesn't blow up. It's not a runtime error, but it doesn't do anything good. If I try to print out A here, it's not going to equal 3. Why? Because it wasn't assigned. We didn't use the assignment operator. So if I type in 100, A is still 100, even after this. It doesn't work. So that's wrong. Also, if A equals 3 is wrong, because we should have used 2 equals. And that one won't compile at all. Right. Should be A equals 3. Should be if A equals 3. And who cares about the spaces? Actually, in my exams, I usually say leave off all unnecessary spaces. That just means that the auto grader won't flag it as an error. I go through and I grade them all by hand, so even if you did add spaces to it, you're going to get it right, but it makes it, save some time for me. Alrighty, I'm pretty sure we know this one, but if we have these 3 pieces of data, which one of these is a string, which one of these is an int, and which one of these is a float? What's that one? Yep. You know what I need to do is, there's a program I can use where you log on to a site with your cell phones, and it pops up a little quiz like that, and then you all press the button, that's an int, and then you could race to try to get the most answers, while we show the questions up here. That'd be fun to do. That'd be a fun form of test preparation. But anyways, so that's an int, which means that's a float, which means that's a string. All right. I hope y'all come back, because there is some in class as well. The plus sign does 2 different things based on where it is used. Plus means addition when used with numbers. Plus means concatenation when used with strings. What does that mean? If I type in A is equal to 3 plus 1, what does A equal after that? That's pretty obvious, right? It's doing math. What does A equal? 4. Okay. For some reason, only this side of the class talks. Y'all don't like me as much. Make me feel good, and y'all talk as well. So, what happens if you do this? A is equal to 3 plus 1. Well, these are strings. It doesn't know what a 3 is. It doesn't know what a 1 is. It's not going to add those together and say, oh, that's a quote 4. Instead, it does concatenation. Concatenation means sticking 2 things together. 31. And so that makes it 31. Python does something really funny that it's not that funny, that other languages don't do, which is you can use multiplication on strings and it performs multiple concatenations. I'll show you what I mean. A is equal to Joe Bob. B is equal to 3 times A. Wow, I didn't expect that to work. And then you print B out. Joe Bob, Joe Bob, Joe Bob. Just repeats itself 3 times. You can make a huge string that way. B is equal to A times 1,000. B. Woohoo! Alrighty. All right, if you have some code that looks like this, x is equal to 2 times y. Let's do an input in here. Y is equal to input. Give me a number. Y is equal to int y. Y is equal to 2 times y. Print. Excuse me, x is equal to that. Alrighty, out of all of that stuff, I'm actually going to remove the one that says expression, but there are functions in this code. At least one. Might even be 3. What are the functions in this code? The functions are input, int, and print. Anytime you have a word followed by parentheses, it's a function. Even if you don't know what it means. You know, if I write some code that says something like this, glorple, you know, why? You don't need to know what glorple is. Good thing, because I don't know. But that's a function, because it ends in parentheses. And by the way, the y in that is called a parameter. It's called an argument on this end, but it's called a parameter when you do a DEF. So anyways, we have 3 functions. The input, the print, and the int. Anything with a parentheses after it. What is an expression? An expression is a mathematical formula. There's really more than one expression here. That's why I'm not going to ask it. But that's the clearest expression. Then, what are the operators? We've been using that word, like a multiplication operator, addition operator, subtraction operator. Which of those are we using here? Come on, guys. If I stand over here, will you all talk to me too? What are the operators on this side? I mean on the code up here.
Multiplication.
Yeah, multiplication in this case. And if the equation was a little bit more complicated, like that, then there would be 2 operators. There would be multiplication and yeah, exponent. So those are the operators. So what are operands? Operands are the data that the operators work on. So what are the operands of the exponent? What data is it working on? Come on, guys. I'm sorry, I didn't hear. Right, it's the y. Well, you're right. The operands of this are 2, y, and 3, but the exponent's operands are y and 3, and the asterisk's operands are 2 and the value of that expression. So what are the operands? 2, y, and 3. Like that. One more. We've already talked about this. But what is the assignment operator out of all of these? I've been using the word assignment already, so don't let the silence deafen us too much. It's different than the concatenation no, that's wrong. It's different than the equality, the equals, but it's that. We're in agreement? that assigns the value of input into Y, that makes it the assignment operator. So strictly speaking, you could say that there are more operands here than what we just listed here, because this is an operand of the assignment operator, but I don't really want to go that far. I'm not trying to make it that tricky. So I may not ask about the assignment operator in this context. Alrighty, now we're going to get to some new stuff. And I apologize for throwing some new stuff at you the day before the exam, but we're going to make it pretty simple. Not going to be too many questions over it. There were like 2 pages of questions on it originally. We're going to narrow that down to like 2 or 3 questions. Alrighty, how do you count in decimal? You have an odometer, for example. What does decimal mean? Well, it means floating point when we used it in other places. But decimal means base 10. Base 10 is how we count, because we have 10 fingers. If we had been octopuses that grew out little 8, fingers out of each tentacle, they'd probably use it base 8, and that would be called octal, like an octogram. And we're not going to use octagon. I don't know why I said octogram. If we had only 5 fingers, if we were one-handed, we'd probably call it base 5. Or anyways. So base 10, because we have 10 digits. 0, 1, 2, 3, all the way up to 9. So when we teach kids to count, they go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are the digits of our hand, but they're not really the digits of our math. In math, 0 is a digit. So I could imagine some computer science nerd 3-year-old going 0, 1, 2, 3, and then the teacher counting them off. Anyways, preschool person looking at them weird. So you have your odometer. You're driving down the road. Brand new car, no mileage on it. You drive a mile. That turns into a 1. Turns into a 2. Turns into a 3. You drive 9 miles. Then you get to the next mile. What happens? And we know what's going to happen. The next mile is a 10. But let's break it down a little bit. What happens to this 9 when we go the extra mile?
It rolls over to 0.
It goes back to 0. We go from the highest digit back to the lowest one, and then we add 1 to the next column. So that if you have 999, let's make it 800. 999, you drive 1 extra mile. The 9 rolls over to the lowest digit, you have to carry it. That 9 rolls over to the next digit, you have to carry it. That 9 rolls over to the next digit, you have to carry it, and then one last 1 rolls over to there. I think I was saying 9 carries. That's 1s that carry, not 9s. And we know this in our head. We learned this in the 2nd or 3rd grade or whatever, and so we don't even think about it in those terms really. What if your computer was driving a car, and the computer only had 1 finger? That sounds like a rude computer. So this is base 10. It supports all the digits from 0 to 9. Binary is a numbering system that only has 2 digits, 0 and 1. So you have a binary odometer in your car for some reason. You're a real nerd. You go 1 mile, that turns into a 1. You go another mile, you have maxed it out. There is no 2 in binary. So what happens? The 1 changes into a 0, and we carry a 1. We go another mile, that flips to a 1. We go 1 more mile, we've maxed out that column. We carry the 1 over. I drew the line too high, should go there. 1 and 1 is, we've maxed that one out. Carry it over. We have 1 more 1 to carry, and there. So I drew too many lines for you to see the way it's counting. But 0, 1, 1, 0, 1, 1. 1, 0, 0, 1, 0, 1, so on like that. Yeah, we may as well go all the way out to the end of all 3 bits. Each place is a bit. Computers can only understand off and on at the most fundamental. Even before electrical wires, memory circuits were invented, they had mechanical relays. The mechanical relay was either closed or open, on or off. Or you had vacuum tubes. If it was glowing, it was on. If it wasn't glowing, it was off. When you have current going down a wire, that's a 1. When you don't have current going down a wire, it's a 0. You have a CD. Remember those? You have your aluminum platter. And if the pit is dug into the CD with a CD burner with a laser, that's a 1. And if a different kind of pit is drawn on it, that's a 0. Whatever. Zeros and ones. We could count these out by hand in decimal. That's a 0, that's a 1, that's a 2, that's a 3, that's a 4, that's a 5, that's a 6, that's a 7. And I'm going to transfer to writing notes on Notepad now. So here we go. Binary only has 2 digits, 0 and 1. Each place is called a bit. We also have bytes in computer. A byte is the smallest addressable cell of memory. It's 8 bits. So you talk about how many, megabytes of RAM your watch has nowadays, or whatever. I have a 64 megabyte whatever. Then you also talk about gigabytes, which is a billion bytes. I bought a 260 billion byte hard drive, or I bought a 2 terabyte hard drive, or whatever. The Greek prefixes, indicate the number of bytes. But each byte is composed of 8 bits. Just remember that, because that's probably a question. Put some star next to it. 1 byte is equal to 8 bits. What would half a byte be called? And this is not really a joke. Somebody decided that a half a byte is called a nibble. I didn't invent that. But it's not really a joke. People used to have programs that would call, I can't even remember them. If you had an Apple II or a Commodore or an old Atari and you had a disk drive, if you had a nibbler, it would make more efficient copies of your disk than of your floppy disk than if you had, a more stupid copy program. Okay, so we're going to count them down again. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1. What's the next one, guys?
1, 1, 0.
Yep. 1, 1, 1. And we're going to put their decimal equivalent, base 10 equivalent. That's not a 1, that's a 0. Where have I gone wrong? There were supposed to be 7 values. I skipped a sequence somewhere. Does anybody spot the missing number? And it's not missing on the decimal, the base 10 side. Yeah, I went straight from 1, 1 to 101. My mistake. That should have been like that. I was in a hurry. Okay, it would be a real pain if you had to memorize all these values. I'm going to go to 4 bits now. That doesn't change anything because that's just putting zeros in front of it. But the 4th bit means that you could keep counting up to larger numbers. Don't make me sleepy. Alrighty. So, what would that have to be? If this is a 7, then that would be 8, 9, 10, 11, 12, and so on. But you don't have to memorize these. Even if I ask you, what does 1101 mean? You don't have to memorize it. It's pretty easy to calculate.
Well, wouldn't you stop at 9 and go 8 for F?
You're right if I was using hexadecimal, but I said I was using base 10 because I haven't introduced the term hexadecimal yet. Okay. 14, 14, 15. Okay. So there are 16 different values 4 bits can hold. 4 bits can hold 16 values. 3 bits could hold 8 values, because we count 0 as one of them. How many could 2 bits hold? Just these numbers. So, whoops. Sorry, it's highlighting that stuff over here. But how many values can we hold in 2 bits? That's 4. There's a mathematical formula which indicates how many different values a number of bits is. And that's just 2 to the power of n. Did I goof up? Pardon me? Yeah, why did I do that? 2 bits can hold 4 values. 1 bit can hold 2 values, either a 1 or 2 values, either a 1 or a 0. Thank you for correcting that. So if I had an 8-bit chip, like the chip that was in your original old school Nintendo, then if I wanted to find out the largest number it could count to, or the range of numbers, it could hold like 256. So your Nintendo may have been capable of picking from one of 256 colors, or something like that. It was pretty primitive. If you had 16 bits, like your Sega Genesis or your Super Nintendo, and I know these references are even getting out of date for most of y'all, that would be 2 to the power of 16. 65536. The Genesis had a much broader color palette, as did the Super Nintendo, so you could make better looking graphics. If you had a 32-bit color palette, that's like 4 billion. You know, that's moving into like PlayStation territory, where you know, the screens could be, you know, photorealistic or whatever. Back in the oldest days of the PCs, you know, you had something that may have been only able to draw 8 colors on the screen or 16 colors on the screen, and it was a real accomplishment to get 256 colors on the screen. And then he added a new video card to it that would make it far better. It's just a number of bits that could be used to store the colors. Alrighty, so how do we convert these to these without memorizing them? Because I don't want to memorize that 1101 is equal to 13. We got to go back to our odometer here. Say you had a number here, 8,321. What is this column called? That's the ones column. I wish I hadn't drawn this so tall. That's 10 to the power of 0. As I mentioned, anything to the power of 0 is 1. What's this called? The tens column, which is 10 to the power of 1, because any number to the power of 1 is itself. This is the hundreds column. It's 10 to the power of 2. This is the thousands column. I'm probably writing too small. Sorry. 10 to the power of 3. So if you have a binary odometer with 4 places, this is still the ones column, because that's 2 to the power of 0. This one is 2 to the power of 1. That's 2 to the power of 2. That's 2 to the power of 3. Well, what's 2 to the power of 1? Any number to the power of 1 is itself. So it's 2. What's 2 to the power of 2? 4. 2 to the power of 3. Well, you just keep doubling. 8, 16, 32. Just like up here, each time we multiplied by 10, we just kept adding zeros. When you're doing binary, you just keep doubling. So if I had the number 8321, that means 8 times 1,000 plus 3 times 100. I'm going to change this to a 0 just for effect. Plus 0 times 10 plus 1 times 1. And then we add those up and we miraculously get 8301. We have triumphantly converted base 10 to base 10. Big whoop, that's like translating English to English. But we're going to convert a number from binary to base 10 now. We're going to convert the number 1010. So this means, here's our places, 8421. So if I type in 1010, that means 1 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1. If you wanted to shorten it, that just means 8, because of the 8 right there. There's no 4, so let's skip that off. Plus 2. There we go. 10. So that 1010 is equal to 10, which if I scroll back up there, turns out to be accurate, thank goodness. What about 0111? How many 8s do we have in 0111? We have none. So that's 0 times 8. Plus, how many 4s do we have? 1 times 4, how many 2s? Yeah. And how many 1s? 1. Okay, so that's equal to 4 plus 2 plus 1, which is 7. We get that pretty easy. 0, 0, 0, 0 is 0. Has no 8s, 4s, 2s, or 1s. You know, 1, 1, 1, 1, that's an 8 plus a 4 plus a 2 plus a 1, which is 15. Alrighty, here's where we get out Notepad, Python, Word, whatever, because I'm going to give you all a sequence of numbers that I want y'all to add up. Not add them up, convert. Tell me the decimal equivalent. This is binary. We want to convert to decimal, base 10. So don't just blurt it out. Type those numbers in and then do something like this. I'm going to do the first one too for you. Well, that's pretty easy. That's a little too easy. There. It's easier if you put that 8421 up there so that you have a visual clue. And this top one is an 8. There aren't any 4s, but there is a 2. So that's equal to 10. Do the rest of them the same way. So you're a bit of a computer pro because you knew hexadecimal. All right, I think people have stopped typing for the most part. Nope, not quite. What is this one? Don't just give me, 12 or whatever it is, and that's not right. What are the numbers I add up? What's that one? What's that one? So it's 8 plus 1 equals 9. How about this one? What are the two numbers we're going to add up? 4 and 2, so that's a 6. Here, how many numbers are we going to add up?
8, 2, and 1.
We're going to add up 3. 8, no 4s, 2, 1. So 8 plus 2 is 10, plus 1 is 11. Alrighty. If we had a 5-bit number, like that, what do you think this 5th place is? Well, if that's an 8, a 4, a 2, and a 1, what's that place going to be? 16, yeah. I can't write 16 in one, little digit in this. But anyways, you get the idea. So, what would 10010 be? I heard somebody say it. You're getting to the point where you don't even have to think about it much. What two numbers do you add? 16 and 2. Right. Okay, converting backwards. I'm not going to ask you this because it's kind of an annoying process. But suppose I had the number 12 and I wanted to convert it to binary, base 10 to base 2. There's more than one way. Usually what students do is they go, okay, well, what's the largest one that'll fit? Okay, an 8 would fit in there. I could put a 1 there, and then I'm going to subtract 8 from that, and I'm going to get a 4, and okay, that's going to be another 1. Instead, algorithmically, what you do is you keep dividing by 2, and then you write down the remainder. 12 divided by 2 is, and you really don't have to take these notes. This is kind of just, 12 divided by 2 is 6 with a remainder of what? 0. Okay. So what's 6 divided by 2? That's 3 with a remainder of 0. And then 3 divided by 2 is 1 with a remainder of. And then 1, you saw what I was doing. I was taking that number, moving it back over there. Divided by 2 is 0 with a remainder of 1. So, and then you write them in opposite order. So that's 1, 1, 0, 0, which if we add them back up is an 8, a 4, and that's it. So we worked our way from 12 binary to 12 in base 10 to 1, 1, 0, 0 in binary. I'm not going to ask you to do that, but I am going to ask you to do this kind of stuff. And it's really not too rigorous. If you need a reminder on test day, I may do an example again. Don't be shy about asking, especially since we only covered it in one lecture. That's about it. Take your Word document, make a Dropbox for it. Alrighty. Refresh your Dropbox. You'll see Dropbox K. And we are done. Any questions? I am so sorry. Pardon me?
I was just following along. I didn't put anything really.
Upload a blank document. I'll know you did it.
Yeah, same with me. I was just.
Okay, if you didn't type in anything, just upload a blank document. I don't care. I know y'all all were here and that you know how to do it, right? I'll trust that you know how to do it. All right, one more reminder. We don't come to class Monday. I'll be putting Charles Manson on trial or whatever I'm going to do in jury duty. And I'll see y'all on Wednesday. We're not going to assign any homework in the next day or so that you don't have to do homework over spring break.